And now I'm going to hand it over to Paul Kraus, coordinator of the Concrete Materials TRG. Paul?
Thank you, Laurel. Appreciate that. Today's webinar is entitled Impact of Portland Limestone Cement, as brought to you by the Concrete Materials TRG. In today's webinar, we are highlighting two new staff members, Mark Niemuth and Elizabeth Nadelman. Mark Niemuth joined WJE earlier this year in 2016. Some of you may have met Mark during our company conference, or if you visited his table at Live Lab, where he was demonstrating the effect of various admixture interactions on cement paste properties. Mark brings extensive experience in the cement and concrete industry with a focus on materials performance and evaluation. During the last decade, working for a major cement producer, he provided technical services and product development, which included development and commercialization of Portland limestone cements for North American markets. Mark earned his PhD from Purdue University researching optimization of cementitious materials for performance in concrete. His specific areas of expertise include new product development, cementitious materials and applications, testing, statistical analysis, and troubleshooting concrete and cement performance issues. Mark is a very valuable resource to WJE, and we are very happy to have him on staff at the JTC. Elizabeth Nadelman joined WJE just this June and has already been involved with a variety of projects related to concrete durability, service life modeling, and materials evaluation. We had to wait for Elizabeth to join us for several months while she completed her PhD research at Georgia Institute of Technology, where her research focused on the early age properties and long-term durability of Portland limestone cement-based materials. We are very happy to have Elizabeth at the JTC and appreciate her willingness to share some of her research findings with us today. So, what is Portland limestone cement? That's what we're here to learn about today. In the future, if one of your clients asks you if you've heard about diluting Portland cement with ground limestone, or if you've heard about type 1L cement, you can answer that yes, you have heard about Portland limestone cement from this company webinar, and that WJE has experts in our JTC that understand its manufacturing and have researched the effect it can have on concrete performance. It's also a timely topic as environmental and cost pressures increase in North America. We must have an understanding of what changes are being made within our industry and how they might affect our practice, whether it's writing a specification or solving a concrete materials-related construction problem. Further, as we focus our consulting efforts overseas, we need to understand the materials being commonly used in Europe and elsewhere. So unplug your phones and close that other browser window open on your desktop, and please welcome Mark and Elizabeth.
Thank you, Paul. So this is Mark Niemuth. So what we're going to be doing today is we're going to be talking about Portland limestone cement, as Paul already introduced the topic, and we're going to talk a little bit about the concrete, how they impact concrete properties, and then how they also impact specifications and standards and what's going on in the marketplace, and what will likely happen in the marketplace over the next few years. Okay, so just a brief outline. So I'm gonna start with a history and a background of Portland limestone cements, and then Elizabeth is going to be talking about the concrete properties, and then I'm going to come back and talk more on the business marketplace side and how Portland limestone cements will impact the market. So, history and background of Portland limestone cement. So let's start with what is Portland cement. So cement is that very basic, cement's that powder that goes into concrete. So where does cement come from? So what a cement manufacturer is, they'll dig up some rocks, a lot of limestone, and a little bit of other materials to get the exact right chemistry, and then they'll grind those rocks up and then into a fine powder, which we call kiln feed. So it's just very fine. And then they'll stick that into a kiln and heat that kiln up to 1500 degrees and move that kiln feed or that finely ground rock through there. And what comes out is clinker. But at 1500 degrees, you also get a lot of other things, and mainly emissions. So CO2, SOx, NOx, mercury, things that are regulated by governments. So And then next what you do is you take that clinker and you grind it up in another ball mill, and you add usually gypsum or some sulfate source, and that's ground into very fine powder into what we call Portland cement. Portland cement is it reacts with water to get hard, and Portland cement is a specific type of chemistry. So what is Portland limestone cements? So when a cement manufacturer is going to make a Portland limestone cement, they're going to take a portion of that limestone that they would have ground up and then put through the kiln and produce some emissions with. They're going to take a portion of that and skip that burning process and just put it into the finished mill and grind it up with the clinker and the gypsum. So that's basically what Portland limestone cement is and how it's made. So a little bit more detail into Portland limestone cement. So it's Portland cement with at least 5% limestone addition. Portland cements with less than 5% limestone addition are just basically considered Portland cement. The less than 5% is just an addition you can have. So this finely ground limestone, it'll replace a portion of your Portland cement clinker, and that replacement of the clinker is a big deal because of those emissions and the energy required to make that clinker. And it's generally used instead of Portland cement. So if you've got a type 1 Portland cement, you would replace that with a type 1L or a Portland limestone cement. And at least in North America, it's designed for equivalent 28-day strength to Portland cement. So this was a decision by the cement manufacturers to introduce Portland limestone cements into the market. They said the easiest and the fastest way to introduce this product is to give it equivalent performance to the product we already sell today. And the real reasons and the driver for the cement manufacturer, and the cement manufacturer is probably the one who's going to be seeing the greatest direct benefit, is cost and sustainability. By reducing that amount of energy they're putting into burning their materials in the kiln, you're reducing the amount of clinker you have to make, you're reducing emissions, you can lower your costs, and you put yourself in a better position as the regulatory industry changes, and there's more, typically we're seeing more and more regulations, not less and less regulations. So they're looking to the future with these Portland limestone cements. So this finely ground limestone that goes into Portland cements. Finely ground limestone is not a new thing or something that's unheard of in cementitious materials. So I already mentioned Portland cement, you can have less than 5% limestone in it. We have Portland limestone cements. And at least in North America, those are defined as having between 5 and 15% limestone by mass of cement. In Europe, where they've got more experience with Portland limestone cements, they're at between 5 and 35% limestone. When you look at masonry cements, for example, they're 30 to 50% limestone. Those aren't necessarily what you would use in concrete, but they are in the construction industry. And those are all products that are produced by cement manufacturers today. You can also get finely ground limestone added into the concrete by the concrete producers. Generally, that's through ground calcium carbonates. And these are generally less than 35%, and they're a replacement for Portland cement, similar to the idea of supplementary cementitious materials like fly ash or slag. And then you can also get finely ground limestone just from fines coming from your limestone aggregates. And those aren't necessarily a replacement for Portland cement, they just come along. So finely ground limestone is not necessarily a new thing in concrete. So specifically about ground calcium carbonates, because ground calcium carbonates, in terms of composition, they're very similar to Portland cement. So you take a ground calcium carbonate, let's say, and replace 15% of your Portland cement, and you compare that to a Portland limestone cement with also 15%. So they're similar in terms of composition, but the performance is generally different. Because of the cement manufacturer produces the Portland limestone cement, they're going to increase the strength by grinding materials finer, and Elizabeth is going to go into this a little bit more. But what you see is that with some carbonates, when you're just adding those on top of your regular Portland cement, you'll get a reduction in strength, but you get this improvement in rheology and you lower your heat, and those materials are generally used for self-consolidating concrete or maybe controlled low-strength materials like flowable fills. And a lot of the reason for that is the price and then availability and the reduction in strength performance for the concrete is why you don't see a lot of those. But they are available in some markets, especially where you see a lot of SEC work. So some countries over in Europe especially, where they do a lot more self-consolidating concrete, you'll see those a lot more. So they're similar, but there's a few important differences. But most of the rest of the talk will be focusing on these Portland limestone cements, not necessarily ground calcium carbonates. So I already mentioned Europe a few times, but so in terms of history of specifications for Portland limestone cement, so there's been specifications in Europe since the 1970s in certain countries allowing the use of Portland limestone cements, and then when the EN specifications or the European norms came out in 2000, they had in there two different types of cement, SEM2A and SEM2B, with between 6 and 20% limestone and 21 and 35% limestone. About 8 years ago, the Canadians through CSA, the Canadian Standards Organization, they started allowing 15% limestone in their cement specs. And then a few years after that, the concrete specifications came up to speed and accepted the Portland limestone cements. And those are used as an alternative to their generally used Portland cements. In the U.S., in 4 years ago, the blended cement specification for ASTM C595 adopted Portland limestone cements between 5 and 15%, so mirroring what the Canadians had done. And they've always been allowed under the 1157 spec, which is a performance spec, but there's relatively little acceptance of that performance spec in the specifying community. And then in 2016, going back to ground calcium carbonates, or this year, there was a material specification just recently approved in ASTM for ground calcium carbonate material. So one of the questions that you could have is, so why is Europe up to 35% and North America only allowing up to 15% limestone? And a few of the reasons are it's a conservative step. The construction industry is a conservative industry, so they're going from, we'll allow 5% up to 15%. And then the other thing is that the approach that the North American manufacturers have taken is to try to get to equivalent performance. And when you get above 15% limestone, to higher and higher percentages of limestone, it gets harder and harder to get equivalent strength at 28 days. And so if you were talking about producing a 20 or 30% limestone cement, it would be very difficult for the cement producer to grind that cement fine enough to get the equivalent strengths. So that's some of the reason behind why North America has lower limits than Europe. Okay, and so we've got some material specs, and then we get into codes and guides through ACI. So ACI 318, 301, 331, they all reference ASTM versions of 595 that allow Portland limestone cements. ACI 350 references an earlier version of 595, so it doesn't allow Portland limestone cements yet. And then ACI 211, they've got a guide for proportioning with ground calcium carbonate. There's not necessarily a guide for proportioning with Portland limestone cements because you use them the exact same way you would use Portland cements. And then the 2015 building code references ACI 318, the 14 version, which references ASCM 595. So the building code also allows Portland limestone cements. But the building code doesn't necessarily allow ground calcium carbonates yet because it doesn't have any references to that. That's not referenced in ACI 318, and that new material standard for ground calcium carbonates is not referenced in 318 yet. Okay, so I'm going to hand it over to Elizabeth.
Thank you, Mark. Hi, everybody. This is Elizabeth Nadelman. I'm going to be switching gears a little bit and start talking about the impact that Portland limestone cements will have on concrete properties. So first, I want to talk about this idea of equivalent performance that Mark has previously mentioned. This is where the cement producers are specifically using the fineness of the Portland limestone cement to manipulate its properties so that it does have equivalent compressive strength at 28 days to traditional ordinary Portland cements that many of you are familiar with. Fineness itself heavily influences a lot of the fresh and hardened properties of concrete, especially Portland limestone cement concretes. Things like workability, the rate of strength development, the ultimate compressive strength that you get at certain ages are all affected by fineness. And then there's also issues related to things like shrinkage and durability, which could have some more long-term effects that are also related to the fineness that the Portland limestone cement is ground to. So in North America, like Mark was saying, typically we grind our PLCs or Portland limestone cements to a higher fineness to achieve this equivalent performance. So what I'm going to show here, and this is going to be a couple illustrations, is a graph of what's called the Blaine fineness of the cement. It's essentially like a surface area. It's a measure of how fine the cement is. So higher numbers are representative of finer cements. And I'm going to be plotting this parameter as a function of the total grinding time or grinding energy that's required to make your cement achieve a certain fineness level. So first we'll just show traditional Portland cement. Essentially what you're grinding is the clinker. There's also some gypsum in here, but I'm going to ignore that for the purposes of this illustration. As you grind the clinker longer, it becomes finer. Typically, these are ground for ordinary Portland cements till they get a fineness of about 400 square meters per kilogram. But you can have a wide variety of finenesses. This is just typical for a type 1 or type 1-2 cement. If now we're talking about Portland limestone cements, we're going to grind this clinker, but we're also going to simultaneously grind the limestone because they're both being put into the grinder at the same time. The limestone is a softer material, so it's a lot easier to grind, and it ends up getting ground to a higher fineness than the clinker does. So you get distributions that would look something like this, and if you give a weighted average of those two values, you get a Portland limestone cement fineness that varies sort of like this red line that I've drawn here, where it's higher than the clinker, or it's finer than the clinker itself, but not as fine as the limestone because it is a weighted average. Now, if we look at the Portland limestone cement at a fineness of 400, so the same fineness you would have a traditional Portland cement, what you see on this graph is that the clinker is actually a coarser clinker than what you would have in a typical Portland cement. Its fineness is 320 compared to a 400 clinker fineness that you would have in a typical Portland cement. So what does this mean? Well, the coarser your cements are, the slower they're going to react You're not going to get your strength development as quickly, and you might not even get as high strength overall because your hydration reaction might be a bit slowed down or prevented from actually reaching completion if you have the coarser clinker particles. So what the producers do, this situation would cause the Portland limestone cement to not reach the equivalent strength. So the producers will increase the fineness by about 100. So say we're going to increase it by 130 now to 530. What you see here is that the clinker fineness is now much closer to what you would have in a typical Portland cement. And so that way you're able to get similar reaction rates because your clinker is now similar to what you would have in a Portland cement. And so that's how you get those equivalent compressive strengths. One of the interesting features of a Portland limestone cement is because you have all of these fine limestone powders, that actually enhances these reaction rates. So you do get a little bit of a faster reaction rate at very early ages, which we'll see later on contributes to higher strength gains at earlier ages. In terms of the fresh concrete properties, if we're talking about these PLCs that are ground to equivalent strength, so these finer PLCs, what we typically see in terms of workability is that we've got a broader particle size distribution because we now have these finer limestone particles mixing in with our clinker particles. These are improving the packing, which improves the way that the particles flow around one another. So our workability improves. You'll see just generally it's a lot easier to work with these PLCs. Bleeding is going to be reduced. Again, this is due to these particle size distributions. If we have a higher surface area, so our higher fineness, we're going to have a reduction in the amount of water that can be risen to the top. The setting time of PLCs, which I'm showing on the figure to the right here, typically we see either similar setting behavior in the PLCs or slightly reduced ones. And these reductions in setting time go back to the idea that we're increasing our reaction rate. So the cement is hydrating at a slightly faster rate. So these early ages, we get stiffening and setting at slightly faster times. And then finally, the heat of hydration, again, because we're increasing the reaction rates, this heat of hydration will increase slightly at earlier ages, but if you're looking at heat of hydration, say over a 7-day period, it's going to be very similar to what you would have in an ordinary Portland cement. But your 1- and 3-day heats of hydration might be a little bit higher. Looking now at the hardened concrete properties, we've talked a lot about this idea of equivalent strength. So just to further support that idea, I have a graph to the right that shows on the vertical axis the compressive strength of Portland limestone cement, and on the horizontal axis the compressive strength of an ordinary Portland cement that was made from the same clinker without the limestone. So same chemistry of these cements, and what you see is that at one day, the Portland limestone cement concrete is slightly higher in strength, not too much higher, but marginally higher in compressive strength than the ordinary Portland cement concrete. But by 28 and especially beyond 90 days, you see that they're essentially equivalent in strength, and that's by design. As Mark and I have both mentioned before, the North American cement producers design these cements so that they achieve equivalent strength, and you can see from this data that that's indeed how they perform. Overall, the other mechanical properties that you probably deal with on a day-to-day basis, the compressive strength, tensile flexural strength, and the modulus of elasticity, these are all, again, going to be very similar between Portland limestone cement concrete and ordinary Portland cement concrete, again, by design, because these were designed for equivalent performance. The one mechanical aspect that is going to be different is shrinkage. Early age shrinkage of these Portland limestone cements does vary depending on the fineness of the cement. If we have a very fine Portland limestone cement, one with a Blaine of, say, 600, compared to the 500 that we had been talking about before, you will get higher amounts of drying shrinkage, autogenous shrinkage, which could lead to early age cracking in your concrete. However, for typical Portland limestone cement, the shrinkage is again going to be similar or even slightly reduced compared to an ordinary Portland cement. Now I'm going to switch gears and talk a little bit more about longer-term behavior, the durability of these Portland limestone cement concretes. ACI 318 specifically calls out durability requirements for external sulfate attack, chloride ingress, and freeze-thaw resistance of concrete. I'm going to focus on these three because they are the three that are most affected by Portland limestone cements. However, there are other durability issues for concrete that are worth considering, but they're not as affected by Portland limestone cements as these three are. So just keep that in mind. First, we'll talk about external sulfate attack. So what is external sulfate attack? This is a reaction between sulfates, which can be inside soils, groundwater, seawater, wastewater. It's an interaction between these sulfates and the cement matrix of the concrete. And what happens is these sulfates will attack the cement matrix, and they form a material called ettringite, and this is the classical sulfate attack form. This ettringite will cause an expansive reaction that leads to the progressive deterioration of your concrete, typically something you don't really want. There's another type of external sulfate attack called the thomsite form of sulfate attack, and this is slightly different than the ettringite form. It requires low temperatures, typically in the range of about 32 to 50 degrees Fahrenheit or 0 to 10 degrees Celsius, and it's a reaction between sulfates in the soil and carbonates, which we now have in our cement, or in our concrete because of the calcium carbonate or limestone in our cement. So the sulfates, the carbonates, and moisture will all interact with the cement matrix in your concrete, and they form this thomsite that causes your concrete to become mushy. Again, something you don't really want. Now, thomsite sulfate attack typically doesn't occur unless conventional sulfate or classical sulfate attack also occurs. However, because we do have sources of carbonates built into the cement in our concrete, this is something that also should be on your radar if you are going to be working with Portland limestone cements in colder climates. As far as the effect of Portland limestone cements on sulfate attack resistance, the classical sulfate attack Portland limestone cement generally will reduce your sulfate resistance. However, just like with ordinary Portland cement, these effects can be mitigated by using some SCMs, things like slag or a Class F fly ash. The thomsite sulfate attack, again, it follows only if you also get classical sulfate attack typically. Again, can also be mitigated by using SCMs. This form of sulfate attack, it's been extensively demonstrated in the lab, but it's not extensively found in the field. It doesn't necessarily mean that it doesn't occur in the field. However, there's not very much documentation of it happening in the field with Portland limestone cement as of yet, but it is something to be aware of. With that in mind, currently the ASTM C595 specification doesn't allow PLCs to be classified as sulfate resistant. You might be familiar with the sulfate resistant designation for other types of cement. However, currently PLCs cannot receive this designation, but there is a proposal in ASTM and AASHTO to allow this designation as long as it can be shown that these cements have satisfactory performance when tested under the ASTM C1012 sulfate resistance test at room temperature. This proposal has recently passed ASTM voting, but they're waiting on AASHTO approval before it can actually be implemented into the specification. Canadian specifications under the A3001 material specification does allow sulfate resistance designation for Portland limestone cements. However, these Portland limestone cements must be blended with a pozzolan like fly ash or silica fume and slag. And they can only receive this designation if they can demonstrate satisfactory performance at both room temperature and 40 degrees Fahrenheit under this, or under a test that's similar to the ASTM C1012 test. Another type of durability issue that's frequently encountered is chloride ingress, important especially for corrosion resistance. Chloride ingress rates in PLCs that are produced in North America are similar to those, similar to the chloride ingress rates for ordinary Portland cements. What I'm showing in this graph on the right are the diffusion coefficients. It's the ratio of diffusion of chlorides, so how quickly the chlorides can enter the concrete. It's the ratio of that for the Portland limestone cement versus ordinary Portland cement. The values higher than 1 mean that the Portland limestone cements are worse. The chlorides can enter faster. And what you see is most of the dots fall right around the 1 or equivalence line. So these are North American cements. The ones that I've circled in blue are actually European cements. So these are produced slightly differently than the ones in North America, or can be. They have the higher limestone addition rates as well. And what you see for these European cements is that the diffusion rates for the Portland limestone cements are actually higher. So you have a little bit less chloride resistance for these European cements. And the effect is magnified at higher water cement ratios. So that's where you're getting these ratios of 3 or higher, or at high water cement ratios like 0.6. Another measure of chloride ingress is the electrical conductivity of the concrete. This is taken as an indicator, an indirect indicator of the concrete's ability to resist chloride ingress. And in terms of Portland limestone cements versus ordinary Portland cements, there are really no significant differences when measured by the rapid chloride permeability test, which is ASTM C1202. This test is really commonly specified, so you should not typically have significant differences when you switch between the two cements, despite the potential for differences in chloride ingress rates. The last durability topic I want to talk about is freeze-thaw resistance. And the influence of Portland limestone cements on freeze-thaw resistance is mostly a function of the quality of your air entrainment system. If you have a low or marginal air entrainment system, typically what you'll find is that the Portland limestone cements perform worse than the ordinary Portland cements. They have reduced resistance to freezing and thawing. However, if you have a normal air entrainment system, one that you would have for your ordinary Portland cements, for example, you're going to have similar freeze-thaw resistance as ordinary Portland cements. So what this means then is that the same requirements for the air entrainment system for ordinary Portland cements is going to be applicable more or less for the Portland limestone cement concrete. So because of this idea of equivalent performance. The one thing I do want to point out, however, is that the Portland limestone cements, because of their increased fineness, typically do require a slightly higher air entrainer dosage than ordinary Portland cement concrete. So if you're reviewing batch tickets, for example, and you see higher air entrainer dosages with the PLCs, that's not uncommon to achieve the same air entrainment system. The final thing I want to talk about is how the Portland limestone cements interact with SCMs. We talked about combinations of Portland limestone cements and SCMs in the context of sulfate resistance, and you typically see SCMs used in all kinds of normal concrete applications as well. Portland limestone cements can absolutely be combined with SCMs just like ordinary Portland cements. And there's been reported incidences of what's called a synergetic interaction between these Portland limestone cements and certain SCMs. for example, slag. What happens is when you combine the PLC with this slag, you get slightly higher strength than you would if you combine slag with an OPC, or an ordinary Portland cement. You also get slightly improved durability. However, I do want to point out these improvements are typically small, and you can still realize greater improvements by modifying the water-cement ratio, for example, or by changing your SCM dosage than by really utilizing these or relying upon these limestone synergies. There have also been synergies reported between Portland limestone cements and some sources of fly ash, but this effect does depend on the fly ash source and composition, as well as on the cement chemistry. One of the things you might find, though, is that some state DOTs have seen these reported synergies and will allow higher amounts of fly ash or slag to be used in combination with PLCs than they would with typical ordinary Portland cement. So that wraps up the impact on concrete performance. So I'm going to turn this back over to Mark, and he'll talk about the impact on the marketplace.
All right. Thank you. Okay, so now that we know a little bit about how these materials perform, let's talk about how they impact dollars and cents and what's happening on availability. So currently what you'll see is PLCs are sold the same price or slightly lower than Portland cement, and slightly lower to try to introduce materials into the marketplace, and the cement producers are trying to offer a promotional deal for the first couple of years, get people to buy them. And the cost of the cement producer, they may see some cost savings, or it may slightly increase their cost to actually produce it, depending on their specific production scenario. But what you'll see in the future is that the PLCs will be cheaper than Portland cement. And the reason for this is not that Portland limestone cements are going to get cheaper, it's that it's going to get more expensive to produce Portland cements, and driven by emissions regulations. So it costs more and more to make clinker, and it takes more clinker to make Portland cement than Portland limestone cement. So you'll see a greater increase in the cost of Portland cement than you will see Portland limestone cement. And there is, depending on the plant, a potential to increase the output of the cement plant, so they can produce more cement. So what you'll end up seeing is many markets will switch to a Portland limestone cement, and the Portland cement, your ordinary Portland cement, will become a specialty product. What do specialty products mean? It means there's limited availability and higher cost. So let's talk about availability. So availability today, so there's some limitations for when a cement producer will start making a cement available. So one of the big limitations is specifiers. If no one will use a cement, they're not going to make and sell a cement. So the cement industry has made a big push with state DOTs and to get their acceptance, and you'll see a map there of a lot of different DOTs and kind of their acceptance of Portland limestone cements. One obvious note is in the Southwest, where you don't have DOT acceptance. And if you remember back to what Elizabeth said about the sulfate resistance, there are concerns with sulfate resistance. So California, Arizona, and the Southwest, they have high levels of sulfates in their soil, so that's one reason why they haven't gone to approving those. So those state DOTs are allowing a C595 type 1 out as an alternative to your type 1, 2, or type 2, or type 5, or 1S, or 1P cements that they allow today. The other thing that will limit availability is distribution networks. Cement producers in North America, they're typically set up to sell one major product through their distribution networks and their terminals. So it's either going to be Portland cement or Portland limestone cement, and then the other product is going to be harder to get, or it's going to be more costly to get because of transportation, distribution costs. And then the other kind of variable in here that is environmental and emissions regulations. So places where you see higher emissions regulations, or for example CO2 tax or cap and trade, those are the places that are going to impact the cost of making Portland cement clinker the most, and which will make it more advantageous to use Portland limestone cement. So your Portland cement's going to go up, let's say, 10% in cost because of these emissions regulations, and your Portland limestone cement's only going to go up 7 or 8% for these emissions regulations. So there's a few places, especially in Canada. Some of the provinces have CO2 taxes and cap and trade, and those are the places where acceptance of Portland limestone cements has actually gone the fastest. So I mentioned earlier when I was talking about specifications and standards that Canada was about 4 years ahead of the U.S. So in some major metro markets like Vancouver and Toronto, for example, the conversion is over 50% of the market has gone to Portland limestone cements. And those are the places where CO2 tax and cap and trade has been enacted. Availability in the U.S. is, they're probably, like I said, 4 or 5 years behind. It's on a plant-by-plant basis. One producer stated that they sold over 1 million tons in the U.S. over the last decade. Most of the cement plants you'll see, at the very least, they've done trials to prove that, yes, they can produce Portland limestone cements, and they're ready to produce them when the market is ready to accept them. But you still have these limiting factors, demand, specifiers in your distribution network. So you'll see some of the plants producing Portland limestone cements, but the majority of them today they've done trials and they're ready to produce them when the market is ready to accept them. So to wrap all this up, so Portland limestone cements, they're a sustainability move for cement producers in terms of cost, environmental, and regulatory. And they're designing the materials to be equivalent performance, but be more sustainable. And I believe that PLCs will become more popular in the U.S. and will eventually replace Portland cements as the primary cement in many marketplaces, probably not all, but many. And so what you'll see is more and more specifications or people asking about allowing ASTM C595 type 1L or maybe even type 1T. The T refers to a ternary, so you use Portland cement, limestone, and let's say slag or fly ash. But the biggest concern in terms of performance when you switch from a Portland cement to a Portland limestone cement is going to be on sulfate resistance. And generally the strategy that's been pushed is to offset any decrease in sulfate resistance with SCMs. You can also adjust the chemistry of your clinker to increase the sulfate resistance, but generally it's adjusting with, like what Elizabeth said, a Class F fly ash or slag.